Hello everyone, and welcome to our webinar. My name is Oren Elias, and I am the General Manager of CoderZ. And I'm super excited to welcome you all to our first robotics workshop for STEM teachers. For me, this feels like a big family reunion. As I was browsing through the names of the participants, I was glad to see many familiar names that we have interacted with over the past year. A few technicalities before we begin. This live webinar is being recorded, and we will share it with the audience soon after. The chat will remain open throughout the webinar, so feel free to use it. Our team is here waiting for your questions. To submit a question, simply type it in the question box in the lower corner of the GoToWebinar control panel. We will try to answer some of the questions during the session, and we'll also leave time for questions at the end. You can also tweet using the hashtag STEMinar during or after the webinar. I would like to point out that GoToWebinar screen sharing often requires high bandwidth and significant computer resources, which means that our simulation may appear a bit choppy at times. We hope that the content we have prepared meets your expectations and would value your feedback during and after the webinar in order to help us improve and adjust towards the session next week. One last thing before we begin. We've been overwhelmed with the responses for this workshop, with nearly 800 educators signing up. To show our appreciation and our commitment to bring robotics to everyone, we have prepared an exclusive promotion for all of you attending this workshop. We'll share the details of the promotion at the end of the session, so stay tuned. Leading this series of workshops is our very own Adi Shmorak. Adi has vast experience in teacher training and content development. He has been a first LEGO League head judge for over 10 years and is an advocate for STEM education. So without further ado, please allow me to invite our speaker. Adi, the audience is all yours.
Thank you, Oren, for the warm introduction. I am very excited and happy to see so many teachers here with us, eager to get started with robotics. I will do my best to make this a time well spent. Let's start. For those of you who are not familiar with Intelitech, the company behind CoderZ, Intelitech has been a pioneer of robotics in education for over 30 years. Intelitech develops, manufactures, and markets educational and vocational solutions from middle school to higher education in fields such as robotics, automation, manufacturing, and more. CoderZ is our latest innovation. CoderZ is set to bring robotics to all. This webinar, first in a series of 3, is set to help STEM teachers venture into the world of robotics. While we will start with the basics, by the end of the 3 sessions, you will be able to do so much more. Since CoderZ is online, you will also be able to practice in between sessions. And as Oren mentioned, this webinar is recorded, so don't worry, be happy. In this first session, we will not only get to drive our own virtual robot, we will also try and understand what a robot is, what makes it work and why. We will also see how it moves around and how to control it using code. I know it may sound a lot, and that is why my team is here with me for you, ready to take your questions as they arise. Let's go. Actually, the real question here is not what is a robot, but why. Any robot is built for a reason, to solve a problem. Usually, that problem is not a technical issue, but rather something that impacts our lives, and robots can make it better, like cleaning the house for us or mowing the lawn, so we can spend time doing the things we love. So, if a robot is built to serve a purpose, it would be fair to say that robots are problem solvers. That is my definition for a robot. Not sure everyone would agree, but in education, we need to look at things a bit differently and show students new perspectives. As problem solvers, robots offer a great opportunity to practice problem solving. That is why they are so popular in education. Educational robots are also problem solvers. They help STEM teachers, like yourself, deliver interdisciplinary STEM classes, promote tech literacy, engage students, and I can go on, but I believe you will soon see for yourselves how robots, virtual and real, can transform any class. That is why I prefer to relate to robotics as a learning environment, rather than a subject matter or a topic. Let's dig a little bit deeper. So here is a quick question for you. Is a washing machine a robot? You can write your answer in the chat box. Since the dawn of time, civilization needed clean clothes. I mean, where would we be if we all had to wear dirty, smelly clothes all day long? Washing machines do us a great service, not only saving us trip down to the river, but also freeing up our time so we can work on great inventions like the internet or that spinner fidget. Take a few more seconds to submit your answer. Is a washing machine a robot? Looking at your answers, it seems like our washing machine is not considered to be a robot, but it is still a technological system that solves a problem, and it makes our lives better. Well, that is a slippery slope, though. If the washing machine was also able to, say, pick the dirty clothes off the floor, maybe even dry it, fold it, and even put it back in the closet, then you would have probably considered it to be a robot, and not just any robot, a dream robot. I have 4 kids, so you can understand what that would mean for me. So what makes a robot a robot? Let's find out. For a washing machine to do its job, it needs energy, materials, and data, things like dirty clothes, clean water, soap, and power. These are called inputs as they go into the machine. Every technological system has inputs. The washing machine, like any other technological system, has outputs as well. Outputs are whatever the washing machine outputs, like clean clothes, but also dirty water, noise, pollution, etc. Outputs can also be energy, material, or data. Here is a fun activity for your students. Ask them to name the inputs and outputs of a desktop computer. In this case, the keyboard would be an input and the screen an output. Speakers would be outputs as well, but the microphone an input, and so on. Robots can be described in a similar way. They have inputs and outputs, and these define what the robot is capable of doing. Let's have an even closer look. We'll start with inputs. These are usually electronic or electromechanical devices that can convert a physical quantity to voltage. The robot's controller, which is the brains of the robot, uses this voltage reading when running a program. Don't worry, we will explain this further in the next session when we talk sensors. We will see that with more sensors, there is more the robot can see around it. In this session, we will focus on the outputs. These define what the robot can do. With more outputs, there are more things a robot can do. Robot outputs, in most cases, are used for motion. Robots, unlike washing machines, are more versatile in their ability to move. Whether they are along an assembly line or cleaning the house, the ability to move is a must if you want to be a respectable member of the robotics community. Motion is almost always acquired using electrical motors. The motors convert electrical energy into kinetic energy, meaning they move, or in most cases, they spin. Here is another fun activity. Ask your students to find out how many motors they have at home. Motors are hidden in almost every household appliance. A washing machine has two motors, one to spin the drum and another to pump water. Shaving machines, food processors, the microwave, these all have motors as well. Can you guess how many motors I counted at my home? Any guesses? Excellent. Whoa, 150 is a lot. Okay, I counted 31 motors, and I probably missed a couple. So, using inputs and outputs, robots can sense their environment and act accordingly. This is where we come into play as the programmers. We determine what action the robot will take for different situations. This is what makes a robot stand out from other technological systems, like our washing machine. Robots are programmable to accomplish completely different tasks, making them so much more versatile. While a washing machine will always clean clothes, the same robot can be used to assemble a car or make frozen yogurt. Let's summarize what we know so far. Robots are problem solvers. They have sensors and motors to help them sense the environment and take appropriate actions. When designing a robot, we need to understand the problem so we can equip the robot with the relevant inputs and outputs. Then we can use code to tell the robot what to do. With CoderZ, writing programs is super easy. Let's see how easy it would be to instruct our virtual robot to take action. A few words about CoderZ. CoderZ is an online learning environment for robotics. It offers both a visual and textual Java code editor and a 3D integrated simulation, all within your browser. I strongly believe that robotics should be for everyone, and throughout the years, I've helped schools struggle with the high entry bar for robotics. But even though I've helped so many schools, it would almost always end up by becoming a niche program. Schools were not able to accommodate robotics for every student, in a way promoting the gap between students rather than fighting it. CoderZ is aimed to bring robotics for all by creating an affordable entry point that can easily scale up. It is complemented by coding robots, a 45 hours worth of curriculum aimed for the middle school. We will be using CoderZ throughout these sessions. You will have a chance to look into CoderZ in between sessions and practice. For those that have not yet signed up for an account, no problem. We will share the sign-up link at the end of the webinar, so you can start practicing right away. This is CoderZ's Mission Center. It holds many learning opportunities and is constantly being updated with more missions. I recommend taking the Getting Started walkthroughs at the beginning to get the hang of things. But for now, we will start with the Navigation Part 1 mission. Meet the BrickBot, our virtual robot, compatible with the beloved LEGO Mindstorm's EV3 robot educator model. Earlier, I mentioned how outputs define what the robot can do. Let's focus on the drivetrain for this model, as it allows it to move around in a special way. The BrickBot has two wheels, each connected directly to a motor, which means this robot has two motors, the left motor controlling the left wheel and the right motor controlling the right wheel. There is a ball bearing located at the back of the robot to provide it with balance. This type of drivetrain is very common in robots. It is called a tank drive, and you can find it in Segways, robot vacuum cleaners like the Roomba and Nito, and in many education robots. During the next few missions, we will construct a rule book that applies to our BrickBot, the EV3 robot educator model, and many other robots. Unlike cars that have steering wheels, we have just these two motors. With them, we can control the robot in multiple ways. By exploring these ways together, you will know, by the end of this session, how to make such robots drive around. In this first navigation mission, we need to drive the robot forward. As you can see in the base code, we can control each motor independently. Here is the block for the left motor and another one for the right motor. The robot needs to drive forward, collect all those nuts and bolts until it reaches that target at the end of the path. These blocks make our code, just like Scratch. Writing visual code is very intuitive. All you need to do is snap blocks together. Once your code is ready, you can run it in simulation or download it to the real robot. One of the great things about learning with robots is that robot allows us to raise an hypothesis and put it to the test. This is something students can also do by their own at home, like in flipped classrooms. So here is another question. I will enter a speed value of 100 in the left motor block. "100" would mean top speed. Write down in the chat box what you think will happen when I run this code, powering just the left motor. Will the robot drive forward? Will it turn? If so, in what direction? To the right? To the left? I like asking students to use their imagination before making an assumption. What would happen if we step forward using only our left leg? Write down your answers now in the chat box. Don't rush, you have a moment. An assumption is worth nothing without the means of putting it into the test. CoderZ enables us to immediately put our assumptions to the test. By running the code in simulation, I'll click Run. By running the code in simulation, as you can see, the robot is turning to the right. The left motor is pushing the robot forward. But the right wheel is holding it in its place, resulting in a pivot turn around the right wheel. To see it clearly, let's activate the trail option. It will instruct the robot to leave a trail below its center of gravity. We can now clearly see how the right wheel is the center of this circle. So, we analyzed a particular behavior based on which we can formalize a general rule, saying driving just one motor will turn the robot towards and around the other motor. To validate this rule, let's test it out against another particular case. Let's see if this rule applies to the right wheel as well. Our new hypothesis would be that if we turn only the right motor, the robot will turn to the left and around the left motor. Let's run the new code. Great. We now know how to pivot turn the robot, powering just one motor. Now, it is time for another hypothesis. What if we drive both motors together? I'll set both motors to 100. What do you think will happen now? Write down your answers in the chat box and we will try in a second. You can think about walking with both legs advancing at the same pace. Where would we go? Let's run the code. Hooray! Getting it right is always great, but in robotics, it is also great when you make a mistake. Great discoveries happen when we make mistakes. I encourage you and your students to accept mistakes as learning opportunities. CoderZ missions are great for trial and error. You can always try again, and when successful, click Next to take another mission. Let's move on to the next mission. Drive the robot backwards. Use the correct speed setting so the robot backtracks and collects all points. May the code be with you. We just saw that driving the robot forward requires both motors to turn at the same speed and direction. That is another one for the rule book. Driving backwards, which is what we need to do now, is just as easy. Direction can be set using these drop-down menus. Let's try and run it. I forgot to add power, so the robot stops. I'll add 100 for the left motor and 100 for the right motor and run it again. Hooray! Before we move on to the next mission, let's try again and explore a little bit further. Let's see what happens if we use negative power. Let's write our code and put it to the test. I will switch back the direction to forward and this time use -100 for both motors as the set speed. Let's run our code now. Awesome! Negative power changes direction as well. Speed is actually a vector, as it has both direction and magnitude. Before we move on, let's have a look at the rulebook we started. This rulebook we are building together is based on observation we made through trial and error. We analyzed information, applied conclusions, and have moved from the particular to the general and then back to another particular case. Constructing knowledge that way is at the foundation of CoderZ curriculum. Let's use an example taken from our Coding Robots Middle School course. Here is one of our Coding Robots earlier lessons. While you are not familiar with all blocks and commands and may not see yourself as programmers yet, with the Blockly Visual Code Editor and the simulation as an interpreter, reading code is a great practical way to develop computational thinking skills. This lesson is about reading code. Students are asked to figure buggy program. Using the code comments and the simulation, students need to figure out what commands are missing so the robot returns to its starting position. From the comments, we can see that all this program is doing is to drive the robot forward for a while, then turn the robot to the right, then forward, then turn to the right, as its code repeats itself. To fix this code and bring the robot back to its starting position, let's see what we need to do. Let's use the simulation as the interpreter of the code. I run my code and try to find out what is missing. As we can see, we are only missing two actions: turn to the right and then move forward. We already have these blocks available for us, so all we need to do is just duplicate those commands. I'll duplicate this block, which takes the robot forward, as it says so in the comments. Oops, I made a mistake. First I need to turn, and then I'll duplicate this block, which takes the robot forward, bringing it back to its starting position. These comments help me to understand what the code is about, and running a simulation helps me see exactly what it means. If you are already familiar with programming, you probably thought, why not use loops? Once students are introduced to new concepts, such as loops, they revisit previous missions in which they can apply new knowledge. This is very helpful as they already understand the problem and can focus on applying a new and different solution. I hope by now you feel just a little bit more comfortable reading visual Blockly code. Write down OK in the chat box if you indeed feel more comfortable, or ask a question and my colleagues will reply promptly. Excellent. As you can see, we are slowly constructing more knowledge and acquiring more skills. But do not be discouraged if it feels like a lot to take in. With CoderZ, you will be able to practice and experiment whenever you like. And I guarantee you will feel very comfortable in no time. In fact, I can guarantee that while you may make some mistakes along the way, no one will get hurt, and CoderZ will not blow up in your face. In the next mission, we will learn to use sensors. In the next session, we will learn to use sensors so the robot will sense its environment and be more accurate and reliable. Excuse me. Before that, I want to show you something if you feel stuck or want to try from the beginning. From the mission menu, you can easily navigate to previous or the next mission, but can also restart the current mission. If you feel lost, this is a good place to restart. Remember though, this will delete your own code and bring back our base code if available. I will move on to the next mission, Navigation Part 3. While similar to the first mission, Navigation Part 3 requires us to turn the robot before driving forward. Someone, it wasn't me, turned the robot away, and we need to fix it. Luckily, we already discovered how to do this and turn our robot through trial and error during the first mission. We know powering just one motor will make the robot turn to the direction of the steel motor. In this specific case, turning the robot to the left will point it at the direction of our objective. So, to turn left, we just need to power the right motor. If we check the tips, which are located in all missions, we can get some help to guide our way. The idea behind the tips is to help every student succeed. The base code, which is available for us here, helps students feel comfortable with code and promote their confidence. This is important throughout the learning process, and our gamified content provides immediate and positive feedback to make students feel confident and capable. All that remains for us is to find out through trial and error the right timing for turning the robot 90 degrees so it faces the objective. As you can see, the first block has another element added to it which sets the duration of that movement. Let's try it out. We'll first power the right motor to make a left turn, and let's say 1 second. This is in milliseconds, so I'm entering 1000. Once the robot completes this movement, powering the right motor, it will turn left, then we need the robot to go forward. We already know how to do that. Let's use 100 as the set speed for both motors. As you can see, the turn did not cover 90 degrees, so we need to provide it a little bit more time. Tweaking the code like this is something that is always relevant. It's always used even with real robots. In the next session, we will learn to use sensors, so the robot will sense its environment and be more accurate and reliable. Before we move on to the next mission, I want us to take a look into the geometry of the robot's motion. It may sound complicated, but actually all you need is pi. This is another lesson taken from coding robots. It discusses the relationship between the wheel size and the distance covered by the robot with each turn of the wheel. When a wheel completes a full circle, it actually covers a distance equal to its circumference. With real robots, this is an engaging activity in itself. Asking students to prove or disprove this theorem, they'll need to set up an experiment, collect data, analyze it, and, looking at the data, reach a conclusion. We will relate to this as an axiom. The wheels of the LEGO Mindstorms EV3 robot are exactly 5.6 centimeters in diameter. This means, applying the formula pi times d, that the wheel circumference is 17.6 centimeters. This means, according to our theorem, that the robot will traverse 17.6 centimeters for each one complete rotation of its wheels. That, of course, applies to driving forward, both wheels at the same speed. Notice how we are constructing knowledge while using math, science, and engineering. This is interdisciplinary STEM. Moving on, taking into consideration a circle has 360 degrees, we can find out the ratio between the degrees of the wheel and the distance it covered in centimeters. This degrees to centimeters ratio will later on help us control the distance the robot covers using encoders. Encoders are sensors installed on the motor itself that measure its rotation in degrees. Encoders can tell us how many degrees the motor has turned. Dividing 360 by 17.6 centimeters, which is the wheel circumference, gives us a ratio of 20.45 degrees per centimeter. This means that while moving forward, the robot will cover a distance of 1 centimeter for every 20.45 degrees the robot has turned. Understanding this relationship requires practice, which is easy to get using CoderZ. Before putting this newfound knowledge into good use, let's go back into CoderZ and move on to the next navigation mission. We may not be aware of how much we've learned, but we already know what we need to take some more advanced missions. Before we take a look at that scary base code, let's look at the scene. This is our way of analyzing the problem. We can see that following the path of collectibles will bring our robot safe and sound into its parking spot. I can explore the scene further by activating the manual control and taking my robot for a spin. I cannot complete this mission without using code, so we'll try again. What we are going to do next is to use pseudocode. Pseudocode is the bridge between native language and computer code. It is as if we were to instruct our robot using simple words. Looking at the path, we understand we need the robot to follow these basic instructions. Drive forward, turn to the right, and then drive forward again. It is now just a matter of timing. Trial and error is the best way to approach this. Making mistakes is actually collecting information, so do not be discouraged if first we don't succeed. Let's have a go. Our base code already includes part of the pseudocode. We have drive forward, and we already know how to drive forward. We just need to set both motors to the same speed and the same direction. This block we have not seen before stalls the program before moving on to the next part. This will be how long it takes for the robot to reach the junction that we saw. Let's start by trial and error. I'll try with 3 seconds. Let's run our code and see where that brings our robot to. Okay, it went well. Now we need to find out the timing for the right turn. Let's look again at our code. What it says is that we stop the right motor so the robot will turn to the right. We already know that driving the left motor will turn to the right. The left motor is already running. All we need to do is stop the right motor and turn it back on when we want the robot to move forward. This block will turn the robot, the right motor back on. But this block will set the duration for how long the right motor is standing still, for how long the robot will turn to the right. Let's try 1 second and run our code. Hooray! The comments that we added are also very helpful for the students in approaching such missions. It helps them make sense and overcome such challenging tasks. Tips are also available, so while we do provide support, eventually the success is of the student. We are ready for our next assumption, the last one for today. We saw that when the motors are set to the same speed, the robot drives forward in a straight line. What do you think will happen if both motors run, but at different speeds? Remember that we already concluded that if one motor is set to a speed of 0, the robot will start turning towards that motor, and that wheel will be the center of the circle. So maybe this is a similar case. Try to imagine what would happen if the right motor will turn slower than the left wheel, the left motor. Send us your assumptions in the chat. Think about that shopping cart that has one wheel stuck. What will happen, you think? Let's have a look at those comments. Excellent, excellent. Excellent. To try out this hypothesis, I'm going to move on to the navigation part 6. Making assumptions based on past experiences is critical to the learning process, as this promotes higher order thinking skills like synthesizing. To make this a bit visual, I have prepared a code that does something very basic. Give me a second while I open it. This program starts by driving both motors at the same speed, but then starts to gradually lower the speed of the right motor, a bit like applying the brakes, but to only one motor. So after a few seconds, the right motor will stop altogether. We can already foresee what would happen then, having just the left motor turning. Let's run it and observe what happens. As you can see, the robot started in a straight line, but as the power to the right motor drops, the robot curves to the right. Actually, what happens is that the radius of the turn drops from infinity, which is the radius for a straight line, until the right motor stops. At that point, the turn diameter equals the distance between the wheels. What we get is a lovely spiral. Each curve in the spiral correlates to a different right motor speed. We now have something new to add to our rule book. A bit hypnotizing, isn't it? Here is our rule book again. Let's see what we have. Driving both motors at different speeds will drive the robot in a curve towards the slower motor. We can also add that the turn radius is in opposite correlation to the difference in speeds between the two motors. So, the higher the difference, the smaller the turn radius. This is a great rule. We can now apply it to our navigation mission number 6. While there are many ways to solve this mission, the path of collectibles implies that we should drive in a curve. Since we figured out we should just slow down one motor, I will try driving the right motor at a speed of 50, while keeping the robot at the left motor at top speed. So let's set the speed for the left motor at 100 and 50 for the right motor. I'll run the code and let's see what happens. As you can see, the robot is turning, but the curve is tighter than what we wanted. So what do you think? Should I increase the speed of the right motor or maybe reduce it? Write it down in the chat box and we will try again. Okay, so most of you have said to increase. So I'll start with decreasing the speed of the right motor just to spike. Let's write 25. As we can see, the curve is even tighter. So by making a mistake, we actually validated and constructed a new piece of knowledge. If only exams were like this. Now it is time to do right. I may not succeed at my first attempt. Say 80. But that is fine. We know what to do, and all that remains is to adjust the speed to the right value. Almost. Let's add a little bit of speed to the right motor, so the turn radius will be higher and we'll be able to go into that parking. Hooray! So let's have another look at our rule book. This is page 1 of our rule book. Go through it and let us know if it makes sense. These are the foundation of how to move a robot. With this in our toolbox, we can already do great stuff. If you have any questions or would like me to elaborate a little further, now is the time to ask. While you send us your questions, let me show you an example of what we can already do. This code uses only motor blocks and whale blocks. I've added the simulation block that allows us to leave a trail in different colors. I hope you like it. I am not much of a painter, but my robot, as you can see, is a Picasso. Before revealing our surprise, I would like to thank you for your time. I had a great time and hope you did too. To help us improve, I would like to ask for your feedback. Let us know how you found this session and what you would like to see in the following sessions. Write it down in the chat box or send us an email to feedback@intelitech.com. If you enjoyed this session, please share. You can tweet GoCoders and Steminar and tell your friends and colleagues about us. I will see you all next week. Now, Oren, is the surprise ready?
Well, thank you, Adi, for this amazing presentation. Before we open it up for questions, and we received several during the webinar, which we'll address in a moment, so stay with us. We would like to share a special promotion that we have prepared for you. To show our appreciation and our commitment to bring robotics to everyone, we are offering you a classroom bundle at a special price. For orders placed in June, we are offering an exclusive discounted classroom pricing. Instead of $1,800, we are offering to our Steminar participants a unique price of just $600 for an entire classroom of up to 24 students. We're also offering a one-semester pricing for 6 months at $360 instead of $900. This classroom bundle will allow you to use CoderZ with up to 24 students with full access to our coding robots curriculum packed with activities and content. To take advantage of this special promotion, either reach out to us directly for a quote or use the promo codes that we are about to share in the chat box. So we'll be sharing them now in the chat box and also in the question box in case someone does not have the chat box open. We will also share these promo codes in our follow-up email. So these promo codes can be used on our online store. Simply select the quantity of 24 either annual or semester licenses and then use them in the promo box at the bottom of the screen. If you have any questions or comments, please feel free to reach out to us directly or tweet us at GoCoderZ. You can also schedule a one-on-one meeting, and we'd be glad to talk to you by clicking on a special Calendly link that we will now be sharing on our chat window as well. So you can simply click on that link and choose a time slot that suits you, and we'd be more than glad to talk to you and learn more about your programs. So now let's take some time to go through the questions that we've received. Michael?
Thank you, Oren, for explaining how to take advantage of that offer. I'm going to now read some of the questions that people have asked throughout the webinar, and Adi will answer them. So our first question is from Ed. How hard is it to set up CoderZ to work with Android systems we use in FTC?
Okay, that's an advanced question. CoderZ is compatible with two robotics platforms, the Lego Mindstorms EV3 and the FTC robot used in the FTC competitions. That is not very complicated, but it's not something I can explain verbally. On our help desk, CoderZ.zendesk.com, we have support articles that show how to set it up. It is not a complicated process, and it works with the FTC driver app and controller apps.
Thank you, Adi. From a question from Jared. Does this only work with Lego Mindstorm, or could we import this into an Arduino bot?
Well, the first answer, I think, provided the answer for that. Currently, we do not support additional robotic platforms, so the answer would be no.
Okay. Next question from Ed. Will there ever be virtual worlds that match the first games? Back when we used Robotics, they had this option.
Could you repeat that question, please?
Yes. The question was, will there ever be virtual worlds that match the first games?
Okay, we are in discussions with FIRST, specifically FIRST Lego League, as it uses the EV3 as well, to introduce simulated scenes from the competitions. We have not yet reached an agreement on that, but we hope to be able to deliver that in the near future.
Thank you. So the next question is from Jared. Can you write in non-block-based languages later?
Yes, I did not go through that, but just to give you a quick look, every Blockly code has Java preview. This is the Java preview that is created on the fly as I write my code in Blockly. I can either export this code, copy and paste it in my Java project, and then continue working on it, or starting a new project, I can choose to start a Java project programming my virtual robot in Java from scratch. We are working on additional course to further the learning that takes place in coding robots that will focus on Java.
Excellent. We have another question also related to the Blockly code from Madeline. Is this similar to the block code used in code.org?
We are using Blockly. Blockly is an environment developed by Google, which is open source, that allows developers like us and code.org create their own visual code editors. It is a very popular framework to create visual code editors. In fact, Scratch is very similar, and they are probably going to move to Blockly as well. So it's the same in that perspective, but we have created our own blocks within Blockly to accommodate robotics. So it's blocks like the motors, like the sensors, that allow the interaction with the virtual and the real robot.
Excellent. And I think your explanation just answered this next question, but I'll let you answer it in further detail. From Irvin, I've been wondering this the whole time. Can the code that gets built here be downloaded into an actual EV3 brick?
Yes. As I showed, and I'll show it again, we have a couple of buttons. One would run the simulation, as you can see now in my screen, but there is also a download button. To download our code to the EV3, you need Lechos on EV3. Lechos is a Java operation system available for the EV3. Installing it requires a micro SD card, which makes the robot a dual boot, so you can still easily work with EV3G and switch back to Lechos back and forth, and that is the way to work with EV3. As you can see in CoderZ, there's a link to our help center. You can look for articles right within that widget and get results, and there are explanations on how to install Lechos onto the EV3 brick.
Excellent. So the next question is from Marie. I was wondering if this code can be used in FLO competition.
CoderZ is not approved for FLL competitions. We are working with FLL, in discussion with FLL, to try and bring CoderZ to the FLL audiences, but it is still something that is not approved, and we cannot commit to a timeline on that.
Okay. From Andrea, here's an interesting question. Do you want us to work through a certain number of navigation missions before we attend next week's class?
Excellent. So as it comes to homework, and I hope you will like them, we do want you to practice at home. Feel free to go as far as you like, but I suggest do not go too far. Going through the first 8 navigation missions should make you ready for our next session. Those that are interested in becoming a little bit more proficient can go and complete the whole 16 navigation missions.
Thank you. So I have a next question from Susan. What is the time needed in the classroom for doing this program?
Can you repeat the question?
Yes, the question is, what is the time needed in the classroom for doing this program?
Okay, so it depends on exactly how you want to roll this out. The Coding Robots curriculum is over 45 hours worth of curriculum. It is self-paced, so students can progress at their own pace. So it might take a little bit longer or a little bit less. Since CoderZ is online and students can access it from home, they can advance even faster than with regular robots. So it depends on the liberty you provide your students with as to progressing within the content. I hope that gives a clear answer.
Great. So I have the next question from Kelly. I use Vex. Does it work with Vex?
CoderZ does not support Vex, but one of our main goals is to bring robotics to everyone. And seeing CoderZ as a virtual-only solution, we see how students get to experience robotics. And if there is already an existing robotics program, be it Vex or Lego or any other, it usually, from our experience, reserved to a small portion of the student population. Bringing CoderZ to every student creates a much bigger impact. And students going through CoderZ for the first year and only then advance to real robots like the Vex or the EV3 can produce and benefit so much more from the hardware. So while again, CoderZ is not compatible with the Vex platform, we do see a great value in starting with CoderZ to the wider population and then funneling those students that show interest and talent into hardware-related robotic classes.
Great. Next question is from Kurt. Does this have to be run through a browser? Can I download the coding program to run on a non-internet computer?
That is a great question. CoderZ brings a lot of value being online. Students can access it from home. They can practice. You can practice. It also offers great learning management features that we have not gone into. Teachers can see how well their students are doing. That has a cost. It needs internet. So unfortunately, we do not have a desktop installation version for CoderZ. It requires internet connection.
Great. We have a very relevant question to wrap things up with from Christy. Where do I access the 8 navigation lessons to be ready for the next week?
Okay, you'll have to access your CoderZ account. If you don't have an account, just go to gocoderz.com and ask for an evaluation. Once you go into CoderZ, you're going to start a tour automatically. If you don't see the tool, you can access it from the Profile menu and click the Intro tool. It will start directing you where to find the missions. They are located here under this play icon. It will take you to the Mission Center. Here in the Mission Center, you can find the 3 getting started missions that we have, but scrolling down, and I'll exit the tour, you can see more and more missions. You can either start with the first mission, click Next at the end of it, or going back to the Mission Center and choosing a mission of your choice.
Excellent. I think at this point we'll wrap up. If anyone has any additional questions, definitely feel free to be in touch with us. I'm going to hand this off to Oren to say goodbye. Oren?
Yeah, so thank you all so very much for joining us today. We look forward to meeting you again next week on our next workshop webinar. Feel free to invite additional colleagues whom you think can benefit from our workshops, or repost and retweet on Twitter for people to join us next week on the next webinar. Have a great day, and we'll see you next week.
Goodbye, everybody.